Good evening and welcome to the ASV's Astro Talk presentation for October. I'd like to say, in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges the traditional custodians of country throughout Australia and their connection to land, sea and community, and we pay our respects to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander people today. Tonight, the Astronomical Society of Victoria is proud to bring you a presentation by Shanika, I'm going to get it wrong, Galadagi. I've got it wrong and I apologize, Shanika. Shanika will be giving a presentation about how we detect gravitational waves and use these observations to investigate the properties of black holes and neutron stars and highlights from some recent publications. Following Shanika's presentation, we'll have a tour of the October night sky presented by Stefan Nebel, which will focus heavily on the moon as a lead-in to our live stream for this coming Saturday night's International Observe the Moon Night that NASA are holding, which the ASV is a part of. As always, if you're enjoying tonight's stream on Facebook, you can donate stars, and on YouTube, you can donate stickers. All donations, no matter how large or small, are welcome. And if you're watching us for the first time, don't forget to subscribe to our YouTube channel or follow us on Facebook. But before we get started, let's hear from the ASV President, Mr. Chris Rudge. Good evening.
Good evening, Mark. Good evening, ladies and gentlemen. Shanika has got a very interesting talk for us tonight. She is a PhD candidate down at Monash, a young scientist very committed to share her knowledge with others and help others on their scientific journey. She's a member of the Osgrav team and also, I believe, a great friend of our ambassador, Claire Kenyon. So without more ado, where do stars go to die? Investigating the stellar graveyard, observing our universe through gravitational waves. Over to you, Shanika.
Thank you so much. So let me share my screen.
Apologies for the name mix-up.
I've
remembered it now. It's Galadagi. That's closer.
That is totally okay. So I think this is working.
There we go. We've got it now. Screen is ready and the floor is yours.
Thank you so much. And thank you so much for the opportunity to speak here today. I'm very excited to be talking to you about gravitational waves, and particularly how we're observing our universe through gravitational waves and looking at the stellar graveyard. So let's start off our story of gravitational waves, but our story doesn't really start when we discovered gravitational waves. It starts a long time before that. So I'm going to start around 1.3 billion years ago. So here we have a binary black hole. So these are two black holes deep somewhere in space, and they are going around each other. And as they go around, they are distorting the space around it. So you can see the background is kind of wobbling. And as you go on through this video, you can see that these binary black holes merge eventually and the wobbling stops. We can also look at it from purely from a gravitational wave point of view, where you see the black holes merging, and as they merge, they give off these ripples that travel through space-time, and the frequency of the ripples increase as you get closer and closer to merger, and then it stops. And these gravitational waves will travel across space-time until maybe one day they reach us. So this was a gravitational wave merger of two black holes that were around 30 times the mass of our sun. And these are the gravitational waves that were emitted from it. But I'm going to now fast forward a little bit in time to the 20th century. So that's a bit of a long jump. But in 1916, Albert Einstein predicted the existence of gravitational waves. And these are created by accelerating objects in space, such as two massive black holes going around each other. And these gravitational waves will ripple away in all directions from this merger. And these waves will travel at the speed of light. Those were the predictions. And experiments created in order to detect these gravitational waves these experiments started being developed later in the century. So in order to understand what those experiments are and how exactly we look for and can develop instruments to detect these gravitational waves, we first need to understand what happens when a gravitational wave reaches Earth. So we're going to continue that story now. So these gravitational waves have been emitted from this binary black hole system, and they will eventually reach Earth. And so I should mention this video makes the animation quite dramatic of what's happening when a gravitational wave passes through. But you'll see these green glowing things, and that's each wave of the gravitational wave. And you can see the Earth wobbles. What actually happens here is that as a gravitational wave passes through, the Earth is stretched in one direction and squashed in the other. And then it's vice versa. It gets squashed in one direction and then stretched in the other. And this alternates. So for a moment in time, you're taller and thinner, and then in the next moment, you're shorter and wider. So that's what happens when a gravitational wave passes through us. And so I'll just highlight again, this wobbling effect is quite dramatic in this video. So the wobbles that we actually detect are very, very tiny. And I'll get into a little bit later just how tiny these wobbles are. So in order to detect these gravitational waves, we need an instrument that's able to detect these wobbles. And what we can use here is what's known as an interferometer, a laser interferometer. So here I'm introducing LIGO, which stands for the Laser Interferometer Gravitational Wave Observatory. And so this interferometer is very big. So this is an image of the LIGO interferometer in Hanford, which is in Washington. And these arms, each of them are 4 kilometers long. And where these arms meet, there's a base. And at this base, there's a very, very powerful laser, and as well as a photodetector, which detects the light that returns from these beams. And each of these beams are vacuum tunnels. And at the end of these beams, there's a mirror. And so when the laser light goes down these beams, they're reflected and they return back. And so as the gravitational wave passes through the Earth, what will happen to each of these arms is one of them will stretch and the other one will compress, and this will oscillate. And so what this means is that the time taken for the light to reach one end and come back will change. The distance it travels will change because as the gravitational wave passes through, the distance of the arms change, the length of the arms change. So we'll have this change in path of the light beam reaching our detector. So I will highlight this in a slightly better animation. So here we have the laser interferometer again, but quite simplified. So here we have a laser in this cylinder, an object, and then we have here a beam splitter. So this is where the laser light will hit and then split off down the arms of the interferometer. Here we have a photodetector, which is what detects the light, and the light will travel down towards a mirror. The mirrors are indicated by this black circle, and they will be reflected and return. And so these mirrors in LIGO are around 40 kilograms in mass. They're very heavy, and they reflect this light. And so let me play this video. So we have this laser light going back and forth. And as the arm's length change, you can see this blinking like thing happening around here. So let's follow this laser light. So the laser light is split off down both arms. It will be reflected. As it comes back, it will reach that beam splitter again and end up at the photodetector. And so I'm going to pause it right here. You can see when the interferometer is not changing in its arm length, you can see the waves that are hitting the photodetector are perfectly cancelling out, so you don't have any light incident on that photodetector. But when you have the gravitational wave passed through, you'll have a change in length of the arms, and this will be illustrated in a moment. So when the arms stretch and squeeze, you have these waves not perfectly cancelling out anymore, and it changes. So the light that you detect at the photodetector varies over time. And as you get more and more gravitational waves passing through, as the frequency increases, this change happens more rapidly. So the way we detect a gravitational wave is using these interferometers, and they have to be incredibly sensitive to do so. So we have, so LIGO is made up of 2 interferometers. The image I showed before was from Hanford in Washington, and the second one is located in Livingston in Louisiana. And these detectors are separated by 3,000 kilometers. So this is also equivalent to a light distance of 10 milliseconds. So it would take light 10 milliseconds to go from one detector to the other. And so something quite amazing happened on the 14th of September 2015 at around 7:50 p.m. local time here in Melbourne. A gravitational wave passed through, and we got signals in our detectors. So right now they might look like a bunch of squiggles, but bear with me. So the interesting thing here is that the blue squiggle, the signal that was detected at Livingston, that was detected first, only by 7 milliseconds. So the next the signal at Hanford was detected 7 milliseconds afterwards. And one of the things that we can do with this delay time is figure out where this source is on the sky, where it came from. For example, if we didn't have a delay time, it would indicate that the signal traveled the same distance to reach the detectors, but that's not the case here. So it won't be directly in the middle of these 2 detectors. Rather, the sky location for this event looks something like this. So here there's a circle that represents the sky as a sphere, essentially. And so you see this like banana-like shape. And this is showing where we expect the signal to be. This is a big area of the sky. So if someone wanted to search that region of the sky, it would take a while to try and find where this signal came from. But of course, you might not see anything because this was a binary black hole merger. You had 2 black holes in space merging, and it won't emit any light. So we probably won't see anything in light if you were to follow up and look at this region of the sky. But these signals, let's talk about them a bit more. So these signals represent the first direct detection of gravitational waves. So this event was named GW 150914. I will never forget that name. It is ingrained in my mind. So this plot is showing I'll walk you through this plot. So the top left-hand corner plot represents that red squiggle that was on the previous slide. And this was the signal detected in the Hanford detector. And what's quite amazing here is that this bottom left plot is showing what we would expect from theory this gravitational wave signal to look like. So you can probably see, even just by eye, that these peaks and dips line up pretty well. So you can see the way that this signal grows. So you have the amplitude growing over time. You also have the gap or the spacing between the peaks reducing as you evolve in time. And notice that this happens within around 0.15 seconds. So it's a very, very short signal. So it's quite amazing that this squiggly signal lines up really well with theory. But this wouldn't be enough to say we've detected gravitational waves, because maybe that signal was just noise. So what we need to do to verify that that is truly a signal is see whether it appears in our other detector. And we can be safe to know that because these detectors are 3,000 kilometers apart, any kind of local noise shouldn't be impacting both detectors. So here on the top right, we have the signal that we saw in Livingston in the blue squiggle, and the squiggle underneath is identical to the red squiggle. But it's been shifted slightly to adjust for time and the time delay, as well as flipped upside down. And as you can see, again, the location of the peaks line up and the way the peaks evolve lines up, especially in the region where the signal is most coherent. So what this is telling us is that indeed we have detected gravitational waves. And this detection, of course, was made in 2015, which is some time ago now, 6 years. But to me, it's still quite fresh in my mind. So I want to highlight just how amazing this detection really is, though, because the instrumentation here has to be so sensitive to be able to detect these gravitational waves. So I'm going to talk about this strain parameter that I've avoided talking about until now. So the strain is really the fractional change in our detector to length in our detector. And so if we were to calculate the strain, it is the relation, how you calculate the strain is the change in length of the arm as the gravitational wave passes through, divided through by the length of the arm of your detector. So the strain here has a value of 10 to the power of negative 21, which is a ridiculously small number. But if I plug in a few numbers here, so the length of the arm of our detectors for LIGO are 4 kilometers long for both interferometers. And if I plug in that number and rearrange this equation to calculate this delta L, which is the change in length we expect to detect, well, the change in length that the detector needed to be able to detect in order to detect these gravitational waves was 10 to the power of negative 18 meters. So these small numbers are quite hard to comprehend. I find it difficult to comprehend without some context. So let's see. So the size of an atom is around 10 to the negative 10 meters big. And if we zoom down even more into the nucleus, that's got a size of 10 to the power of negative 13 meters. And then if we zoom in even more, this is the size of a proton, and that is 10 to the negative 15 meters. So what does this mean? The change in length that LIGO had to detect in order to see this gravitational wave signal, this change in length was 1,000 times smaller than the width of a proton, which is insanely small. And to put this another way, if you were to take a strand of your hair and say that was the change in length that you were trying to measure with your gravitational wave detectors, you would have to, and in order to detect this strain, you would need to have an interferometer with an arm length that stretches from Earth to the nearest star system, which is Alpha Centauri, which is more than 4 light years away. So meaning light takes 4 years to get there. So that's probably not feasible as a gravitational wave detector, but that just goes to show just how much, I guess, development and work has gone into developing these gravitational wave detectors to make them sensitive enough to detect these really, really tiny changes in length. So it's really an amazing achievement in both engineering and technology, and definitely will be cemented in the history books. But I guess don't take my word for it is what I will say, because this discovery was awarded the Nobel Prize in 2017. So Rainer Weiss, Barry Barish, and Kip Thorne were awarded the Nobel Prize for their key contributions in the development of LIGO. So and the interferometers, and eventually observing these gravitational waves. Because these interferometers weren't created overnight. So in the 1960s and 70s, there were efforts to design these experiments. In the 1980s, they secured funding, and down this timeline, there were many tests that were done. So prior to the observation run that actually detected these gravitational waves, there were tests called initial LIGO, which were looking to analyze the gravitational wave data and see where they could improve the sensitivity of their detectors. And essentially, a lot of testing prior to 2015, a lot of work before we actually detected these gravitational waves. So it is an immense accomplishment. So we can detect these gravitational waves. That's great. But we want to learn about these gravitational waves and what they can tell us. So we have our gravitational wave signal. And there are several stages to when a binary black hole merges. You've got the in-spiral stage, where you've got these black holes moving around in space like this. And then you've got the merger. And at around this point, these black holes are moving so fast, they're moving at close to 60% the speed of light, which is really, really fast. And then finally, we have the ring down stage, where you've got the black hole, it's merged and it's formed a black hole, and it's kind of settling down, it's ringing down. And so you can see the stages of a binary black hole merger in the signal. But more interestingly to me, because this is the stuff that I mainly work on, is trying to understand the properties of the binary black hole from this gravitational wave signal. So we can actually extract properties about the individual black holes that went on to merge from this gravitational wave signal. So, and the properties include the masses of each black hole in this binary, as well as how fast it's spinning, even the direction they're spinning in, so which way they're oriented in the sky. We can tell that from the gravitational wave signal. So we can go from the signal, do some data processing, which I'm not going to talk about today, but this work, using this, after performing this processing, we can extract the source properties of this black hole. So I mentioned that this binary black hole, it was 30 solar masses roughly, each black hole. And so we can see that here in this plot. So this plot on the right is showing the primary mass, which is the mass of the larger black hole in your binary, plotted against the secondary mass. So this is the smaller black hole in the binary. And you can see these distributions that we were able to extract from this gravitational wave signal, as well as this 2D contour. So that it's just these two distributions in a 2D space. So we can, so for every single gravitational wave signal, we can extract the source properties of the binary. And we've had a lot of binary black holes over the years, more than 40 for sure. But I guess binary black holes are great, but I have a slight bias towards a certain compact binary, purely because there's a little added extra with these kind of compact binaries. So with a binary black hole, you just get those gravitational waves. But with a binary neutron star, you get both the gravitational waves and the light that's emitted from that source as it merges, because neutron stars emit light. So fast forwarding a few years to 2017, and so this event called GW170817, which was detected in 2017 in August on the 17th day, this event was a binary neutron star. And so let me walk you through a little bit of the day that went by. So this plot on the right is showing a number of things, but let's start at the bottom here. So here we're seeing the gravitational wave time frequency map. So what this means is you have the frequency on the y-axis, time on the x-axis, and so this is the time till merger that's being shown and how it evolves in frequency. So you may have heard the sound of chirping, gravitational wave signals, and people chirping. So if you were to listen to these gravitational wave signals, it would start off with a low hum and then into a higher pitch. So it would be like a whoop. And that's we can actually listen to these gravitational wave signals because it's in human hearing frequencies if we wanted to. And so after that chirp, we have this merger, and then these three top plots represent the light curves from Fermi and integral, which are looking for gamma rays. And so just under 2 seconds later, there is a peak in gamma rays, which is pretty cool because this is pretty much at the same time. We can consider it to be the same time, given that it's such a short time difference between merger and the detection of these gamma rays. And not only that, if we go throughout the day, we have observations through gamma rays, X-rays, UV to optical. And so here's an optical observation of this event. So this plot here on the bottom left, the left-hand panel shows an image of a galaxy, NGC 4993. And this galaxy was this image of the galaxy was taken by the Hubble Space Telescope earlier in that year, so April 2017. The image on the right is showing the image taken by the SWOPE telescope on the day of the merger. And as you can see, so this red arrow is conveniently pointing at a dot that wasn't there before. And indeed, this dot is showing the kilonova of this event. So a kilonova is where you have the radioactive decay of materials of our processed materials that are ejected from this neutron star as it merges. And it's a very energetic collision. So there are a number of things that happens when a binary neutron star merges. So we had these gamma rays, and now we have these observations in the optical band from this kilonova. And this was detected 11 hours later. As we progress in time, there were also radio observations made of this event as well. And this is the most studied event ever, astronomical event ever, because we had that gravitational wave signal, and we studied it all the way across the electromagnetic spectrum. And this is truly an effort in terms of multi-messenger astronomy, where you're not just looking at one messenger, a messenger being gravitational waves or electromagnetic observations, you're combining both to try and understand what's going on with these objects. And what was really exciting about this event was that there have been predictions that gamma ray bursts come from the merger of binary neutron stars, and this was evidence that indeed we do get gamma ray bursts from merging neutron stars because of this gamma ray signal, and also an evidence for the prediction of the fact that gravitational waves travel at the speed of light. This observation gave us the most precise measurements of that. So this is probably one of my favorite events in gravitational wave land. So here's a video of what was animation of what would have happened in that merger. So you've got the inspiral phase, it merges, and then it gives off a burst of gamma rays. And then you have this bright region, which is the kilonova. So this radioactive decay of materials. And then you have these shocks in the interstellar medium as these particles accelerate through and collide with the medium in space. So that was, I guess, the first binary neutron star that we detected, and we learned a lot from that event. So moving to another aspect of this event. So in order to do optical follow-up or electromagnetic follow-up, you need to be able to figure out where it was located on the sky. So before I showed a banana shape in the sky for GW 150914, so this dark green region. And this dark green region is quite big. But luckily for us, The observation of GW 170817 happened when another interferometer was online. So the Virgo interferometer, which is located in Italy, was online at the time. And so that means we had 3 interferometers operating, meaning we could triangulate the source better. And so this yellow region, as you can see, is a lot smaller than this green region, which was a benefit to us in terms of the electromagnetic follow-up. The search teams, when they were trying to find this, where the event had taken place, which galaxy it was in, they only had to search a small area of the sky. So that's one of the important things about having multiple interferometers. You can localize the source better and potentially find the electromagnetic counterpart to an event. And you'll notice that this 170814 is also quite a small one, which was also using Virgo at the time. And you can see these other sky maps that are really very not constrained. So we have binary black holes. So we have a lot of black holes that we've detected over the years. We definitely have more than 40. And we've also detected binary neutron stars. So GW 170817 was one of them. And we also have another one, GW 190425. There are a lot of numbers, bear with me. And that event was one of the more massive binary neutron stars we've seen, so much so that it's more massive than the typical neutron star binaries we see in our galaxy. So it was kind of a bit of a weird, how do we form such massive binary neutron stars? How do they form? And so a lot of questions are raised whenever we get an exceptional event in gravitational waves. And so we have, I guess, 2 types of observations here, binary black holes and binary neutron stars. And in order to complete this trilogy, we would need a neutron star black hole merger. And that's exactly what we got recently. Well, we announced fairly recently, earlier this year. LIGO and Virgo collaboration announced the detection of 2 neutron star black hole mergers. And so these are mergers where you have a black hole and a neutron star in spiraling and merging. Unfortunately, we didn't see any electromagnetic counterpart for this event. However, then again, there may not be an electromagnetic counterpart for this event. It depends on the interactions and the masses of the 2 components. For example, if you had a really massive black hole compared to your neutron star, you probably wouldn't see an electromagnetic counterpart. But nevertheless, we didn't see an electromagnetic counterpart, which is a shame. But what this detection did do is confirm the existence of these binaries. So from studies that simulate compact binaries, there have been predictions of these binaries existing. And so this discovery confirmed the existence of these binaries with a neutron star and a black hole. So that kind of brings me up to the present day, really, which is a bit of a journey. But we can always look at the individual properties of events, which is pretty neat, and you can learn a lot about them. But my work really focuses on trying to understand the overall population and the properties that we can learn from the population and figure out how these binaries formed and where they formed. Those are the kinds of pieces of information we can learn by looking at a population. So as the title of my talk suggests, I said I'm investigating the stellar graveyard. So here is the stellar graveyard. You may or may not have seen this plot before. The LIGO-Virgo collaboration tends to put out one of these plots every time we have an announcement of a new event. And so to walk you through this plot, so the y-axis is showing masses in solar masses. And so 40 means that you've got 40 times the mass of the sun. That's the mass of the black hole along this line. And so we have here at the bottom in yellow the neutron stars that we've detected via electromagnetic observations, typically radio pulsars. And then we've got in orange the neutron stars that were detected by LIGO and Virgo through gravitational wave signals. And then in purple, we have black holes that were detected via electromagnetic observations. And finally, the blue ones, which you can see there's a lot of, are the LIGO Virgo black holes, so things that we've seen in gravitational waves. And I think that gravitational wave events are pretty great purely because you get three black holes or three compact objects for the price of one event, because you have the two compact objects that go on to merge, and then you form another compact object. And so I guess good value for money, essentially. But with these gravitational wave events, and with so many of them, particularly for the binary black holes, we can start to try and look for the trends in the population and try and understand how these things formed. Is there a relationship between different properties? For example, is there a relationship between mass and spin? Is there a relationship between the spin and where these binaries are forming? And these are the kind of questions we can start to answer with population studies of these compact binaries. And most of my PhD research has been in this area. So I'm going to walk through a few examples of questions that we think about and try to answer with looking at the population of binary black holes and the astrophysics that we can try to extract. So when do we form a black hole? So in what scenarios can we form a black hole? What needs to happen? So you can have black holes forming from the collapse of stars. These would be stellar mass black holes. So in this case, you have a star that's exhausted its nuclear fuel. So essentially, you have a star that has exhausted its hydrogen, helium, and it's fused down to heavier and heavier elements. And now it's down to iron. And iron you can't fuse because it requires more energy in than out. And so there is no longer the pressure to keep the star stable, so it collapses down into and it undergoes a core collapse supernova. So it collapses and rebounds and produces a shock, and those and creates a beautiful kind of image of a shock in space. And what's left behind is a black hole. So we can form black holes through stellar collapse. We can also form black holes, as we know with gravitational waves, through the mergers of other black holes. So I've drawn some purple arrows there to illustrate the direction in which the spin axis is of these black holes. Just like for example, the spin axis of the Earth being slightly tilted, you can have different tilts for black holes with respect to the orbital plane. And so you have these arrows showing the tilts. The size of the arrows represents how fast it's spinning. So the larger the arrow, the faster it's spinning. And so you can have those go on to merge, and then you form another black hole with greater spin and greater mass. So that's another scenario where you can form a black hole. But it's also interesting to look at scenarios where you don't form a black hole. So when do we not form a black hole? And the reason I say this is because when you don't form something, you can try and look for that feature or that process in your binary black hole population. So let me explain what I mean. So for very, very massive stars, say around greater than 130 solar masses, they're massive enough that they're balanced out by this photon pressure from the star. So they're not collapsing due to gravity because of this photon pressure. And so what happens is some of these photons will be absorbed, and these stars will produce pairs of electrons and positrons and release them. And what this results in is the photon pressure decreasing. And so the pressure outwards decreases. And so the pressure around the core, well, the core can't push out anymore. So it starts to compress the core. And this results in higher and higher temperatures, higher and higher energies, to the point where it starts fusing oxygen. And in that case, it results in a runaway process, and eventually the star, there's so much energy that the star completely blows up. There's nothing left behind. And so in this scenario, we don't form a black hole. And so why I wanted to highlight that is that we can try and look for that when we analyze a population of binary black holes. For example, if astrophysics tells us that we expect stars of a certain mass and beyond to not produce black holes, we can look in the mass distribution. So if we were to take the distribution of the black holes for all of the masses, we'd be able to look and see whether there is a cutoff in that distribution. Does it end somewhere? And that could potentially relate back to this process known as pair instability supernova. Looking at this middle scenario where you have these black holes going to form more black holes, you're inheriting the mass and the spin every time you merge. So you'd expect in this scenario, black holes that are getting more massive to have greater spins as well. And so that's something we can also look for when we study populations in terms of understanding the relationship between mass and spin and seeing if there's a correlation there. So these are some of the things we can look for to understand how a black hole formed. We can also look for and try and understand where these binary black holes form. So what I mean by where is what kind of environment did they exist in before they went on to merge. So let's consider a scenario where these black holes form from stars that were in a binary. And so these stars are fairly far away from anything else, so they're only interacting with each other, and they orbit around each other, and they have some sort of spin direction, and they're spinning moderately fast. And as these stars interact with each other, the direction of their spins become less extreme and more aligned. And the reason for that are these tidal effects. So just like you have the moon tugging on the Earth, and we have those ocean tides, you can have gravitational interactions between these stars, and these gravitational interactions make them more aligned. You can also have other scenarios where they undergo what's called a common envelope phase, where they have tidal interactions and drag in the gas that they're in. So a common envelope phase would be where you have one of the stars kind of expand and envelop the other star. Although I won't go into that too much here, but that's another scenario. Please ask questions if you have any. But in this scenario, you have these tidal effects and these binaries become more aligned. And eventually this story ends in a bit of tragedy because one of the stars will undergo a core collapse supernova to form a black hole, so it dies. And in this process, you might have this black hole, this supernova, because it's so energetic, it might give the companion star a bit of a kick, but it's not so much that it will completely separate its companion from itself. They're still in a binary, it's just that the tilt might slightly be more given the kick. And then you have your second black hole formed, and you have this black hole binary. Another scenario where you could form black hole binaries is a case where you just have a lot of black holes whizzing around in the same area. And this can happen in something like a star cluster or a dense globular cluster, which is a lot of stars in a globular shape. And in these dense regions, you can have black holes interacting with each other all the time, potentially, and eventually maybe two of them will capture each other. And so you might be able to notice some of the key differences here. So this first black hole, the spin directions are kind of aligned, they're not so extreme. In the second scenario, there's no reason why these spins should be not that extreme. They could be randomly oriented. And those are signatures we can look for in our population studies of binary black holes. We can see if these binaries have a tendency to be aligned and not so extreme tilts, or whether they have all random tilts. And so in one of my recent publications, this is one of the things that I looked at. I wanted to look at understanding the spin distribution of these binary black holes. So moving on to some of the latest work in the field in terms of understanding the binary black hole distribution for spins. In fact, this paper was actually just accepted yesterday, so it really is recent work. And so let me walk you through these two plots. So the left-hand side plot is the cosine of the tilt that I was talking about in terms of the spin, so how much it's tilted away, how extreme those tilts are. And so 1 represents when it's less tilted, and -1 represents when it's completely flipped upside down. So the tilt is 180. And so you can see here that the distribution of binary black holes, the tilts tend to be closer to 1 than -1. So what this is saying is that our population prefers to be aligned. And so meaning that it's pointing more towards that first channel I was talking about, where you have these stars that die and form binary black holes, rather than that other case where you have black holes interacting in these star clusters, potentially. So that's one piece of information we can extract from these plots. The second plot here is showing the magnitude of our spin, so how fast these things are spinning. And interestingly enough, we're seeing a bimodal distribution. So there are 2 peaks. There's a narrow peak around 0, so this means the black hole is pretty much not spinning. And there's a second peak halfway through this distribution, representing a peak of black holes that are moderately rapidly spinning. And so this leads us back to trying to understand a process that would result in our binary black holes having this kind of distribution, questioning why do we have black holes with such small spins and such large spins with a kind of gap in between. And this can relate back to the interactions between, complex interactions between these binaries as they evolve. And so this is the kind of work that and the kind of questions we can start to answer by studying these observations and these populations, and comparing back to what we think happens in theory. So when our observations in theory match up, then we can be fairly confident that we have the right idea about the astrophysics and the physics that's going on. But until then, our observations will inform theory, and we can continue to develop and understand just what's happening in this binary black hole population. So to finish up, instead of a summary where, given that I've been talking about gravitational waves, how to detect them, and what we've learned so far, I want to give you my gravitational wave wish list. So this is what I want to see in the coming years and what I'm excited about. So I want to see more binary neutron star mergers, because we've had 2, and I'd like more to be able to study and analyze and figure out what the population of binary neutron star mergers is like, if they're different to the galactic population we see. I also want to see an electromagnetic counterpart to a neutron star black hole merger, because, again, we haven't seen one, and it would be quite interesting to see what that's like, and whether, in fact, the theory of, we may not see it for more massive black hole neutron star systems, and in what scenarios we do. So I'm quite excited about that. I've written Funding NEMO. So NEMO is a proposed high-frequency gravitational wave detector that would be in Australia. And so this high-frequency detector would be tailored to understanding more about binary neutron star mergers. And if it's pitched right and funded, then this would be some really exciting science to do in Australia. And finally, gravitational waves from a supernova explosion. So I've been talking about gravitational waves from compact binaries, so black holes or neutron stars merging, but you can get gravitational waves from supernova explosions, where you have mass being accelerated in these explosions at really high rates. So you would expect to see gravitational waves, probably not in the waveform that we're seeing of like the signal growing over time. It would be more like a burst of gravitational waves. And so that's something that I'd like to see in the coming years, decades. So thank you so much for listening, and I would love to take your questions.
So we have a couple of questions. We'll start with Shahir, who wanted to know what's the maximum mass size that can be detected through LIGO. Do we know that?
Oh, that's a great question
Mm.
that I don't know off the top of my head, but I can say the most massive binary. Actually, hang on. I might have some extra slides. So
Holding out on us.
Yeah, no. So these are my lovely backup slides, just in case. So here we have what ground-based interferometers can detect. So rather than the masses, this is more talking about frequencies. So the most massive binary black hole that we detected was GW 190521. And that one was, from memory, around 60, 80 solar masses, and it merged to form a really massive black hole. But that signal was quite hard to kind of analyze because it was such a short signal. It was low frequency. It was more like a whump sound, like a thump whump sound. So as you get to higher and higher masses, they're lower and low frequency, so they will move out of band. So I expect for binary black holes heavier than GW 190521, we probably wouldn't be able to pick them up with our detectors, and we would need those third generation detectors, such as our space detectors, such as LISA, that would be able to detect these more low frequency, high mass events, including mergers of supermassive black holes in between galaxies. Like, how cool would that be?
That'd be pretty cool, actually. We have another question here from Sarah. Can the loudness or amplitude of the gravitational wave help estimate the rate of cosmic expansion?
Ooh, that's an interesting question.
They're trying to stump you.
Yeah, no.
Yeah.
Can the
Making you
amplitude,
think.
cosmic expansion. So I guess cosmic expansion, cosmology, we all love cosmology. So one of the things that we can do with, say, binary neutron star mergers is use them as our kind of a different standard candle to measure this expansion of space. So I'm not sure about the amplitude per se, more the actual number of events, and if we have more binary neutron stars, we'll be able to do cosmology with gravitational waves and get a more precise measurement of the expansion of the universe.
Hopefully we've answered that one for you. Lee wants to know, if we attach enough stars from disparate locations, LIGO should detect it. He's being funny. What have we got? Here we go. Fascinating talk. Thanks for sharing. First time that I get the full understanding that shows the optical view of the event and gamma. How do they know from what area in the sky these came from? So how do we work out where it came from? How do we know?
Yeah, so awesome question. So with sky localization, with the delay time between the detectors, so say, for example, every detector detected it at the same time, you would know that the distance that it has to be to that location would be the same. And so if you have 3 detectors, it would really point to a certain region in the sky, a point, really. If you have, so if the more detectors you have, you can tell from how long it took a signal to reach a certain detector where it should be. Is it closer to this detector or that detector? So that's how we create these localization maps, by trying to figure out which detector it hit first. So which detector should it be closer to? And the more detectors we have, the better we can create that search region. And so the telescopes were searching in that area because LIGO created this sky map and sent it out. It's quite amazing how they do this. This global network where we just send out a notice saying, look, in this region of the sky, we think this is our best guess of the sky map given the localization from these detectors, and they go looking in that region of the sky.
That actually leads into the next question that Lee's got. How much time does it give between a LIGO detection and being able to swing a visual or radio telescope to study the area? So we're just about to say you send that alert out, but how much time do those telescopes that you've alerted have to actually get onto it?
That's an excellent question. I'm not sure I can answer that because I don't have a very good idea of how long it takes for a certain radio telescope to be able to kind of orient itself in the region of the sky. I guess for radio, for example, binary neutron star mergers, you probably don't have to worry too much of being exactly on source quickly because the optical counterpart of radio took days and lasts for days afterwards. But I guess like we're working on the latency of these signals. So there's work being done to try and alert before the merger happens in terms of if you can see the signal in band for a long period of time.
Then you can get the warning out there.
Yeah. But in terms of the delay time between like right now what happens, I'm not sure how quick that is, to be honest. I know it's fairly quick, but not sure exactly how quick.
Stefan, who's hiding in the green room at the moment, said, awesome talk, and it was an awesome talk. Are there plans to build much larger interferometers in the future? Is there a point of diminishing returns? So is there a point where we get so large that it doesn't really matter? You're not going to get any more data. We're not going to learn anymore.
Great question. So in terms of like arm length and things like that, they can help, but one, they're expensive. Two, they're difficult to construct and everything. But in terms of diminishing returns, so I know that these third generation detectors that we're launching into space, they're designed so we can get rid of a source of noise due to the ground, and to be able to see different kinds of sources. I guess I'm just trying to think what the limiting factor would be in terms of seeing certain type of sources, because we can't obviously extend our interferometers forever. But we're like, so there are these pulsar timing arrays that are looking to detect gravitational waves on a much larger scale. So if you have different pulsars in the galaxy, and you can time, they have very precise timing, and the change in time can let you know about the gravitational waves that are passing through the area. So that's how we would go on to like really, really large scales of getting more sensitive to gravitational waves. But I think in terms of what's next of the gravitational wave kind of detectors, we're very much focusing on those third generation detectors such as LISA to be able to look deeper and get rid of that ground noise to be able to detect those gravitational waves. So please do ask me later, maybe, and I might be able to give you a better answer than that. But in terms of different kinds of detectors, there are many. And when we get to, so this is the diagram that I was trying to get to, but I forgot how many animations my slides had. So these really high scale, going down to different frequencies are extremely different to what we're detecting now with these pulsar timing arrays. But great question. I'm not sure how far we can extend these interferometers right now. I'm sure there are right now there's only certain amounts of advancements that we can do to LIGO to get it to design sensitivity at least. But I guess really depends on how much funding we have to a certain degree. But I'm not quite sure. I'm not quite
sure. It's all about
the
funding, isn't it?
Yeah, money.
Money. All right, so we have another great presentation. Thank you. I have a question about white holes, which, as far as I know, are meant to be the opposite of black holes. i.e. they spew material outward. Are they just theorized or do they actually exist? And if so, have we seen or photographed any yet?
So from what I know, white holes are purely theoretical. There's no kind of there's never been any observations of white holes, that's for sure. But I think they're just purely theoretical and not something that people are looking for.
Another one for you. We've got a couple. Everyone's putting. There's a lot of questions coming through. We might have to. We'll have to skip a few, unfortunately. What happens if the spins of two merging black holes were completely opposite? One spinning vertically and the other spinning horizontally. Would they balance out and form one that spins halfway? So you got one spinning, I guess, this way and one spinning that way. I'm not going to try and do it at the same time because I'll look like a fool.
So I can't see what's going on.
So, one spinning top to bottom and one spinning left to right.
One spinning top to bottom, one spinning left to right.
Yeah, so one spinning up, down, and then...
Yeah, so you'd have, I guess, when they merge, you kind of have a combination of those spins. So you would have some, I guess, summing up of it. And also, I'll just add a little bit here. When you have those kind of spins going on, because I just love this. If you have like in plane spins, you have your binary do this kind of processing action. So like you don't just have your binary just going like that. It will kind of do this movement through space when you have these in plane spins. So yes, you have some summing of it when you combine those spins, but they don't, like, given their spin vectors, like they will produce a black hole that's spinning, but they wouldn't cancel out.
Okay, so
assuming I got the orientation.
Could you please tell us more about NEMO? Sounds exciting for current and future students interested in doing research in gravitational waves. I remember I was talking to Paul Lasky about this the other week with Claire, and I told him I thought it was a clownfish. He laughed at me.
Yeah, it's a play on words, funding Nemo. But yeah, essentially, so why I'm excited about it is because it will really be looking in this area of this frequency where LIGO can't go at the moment. Future gravitational wave detectors will be able to, but they're quite a long way down the track. So this black curve, so I should probably describe this plot. So this black curve is essentially everything above that we would be able to detect. So any strain above that at a given frequency. And so this red curve is showing the strain that you would expect from a binary neutron star and where it merges, and then you have the signal from the post-merger. So after merging, you have something formed. We don't know if it's a long-lasting neutron star, for example, or whether it collapses down to a black hole immediately. But essentially, what's interesting here, so if you look at the blue curve here, that's where LIGO will be at design sensitivity. It's missing this higher frequency action. And so what NEMO would be able to do is to be able to detect, keep the signal, the gravitational wave signal from binary neutron stars longer. And that will allow us to better understand some of the matter properties of these neutron stars and essentially analyze extreme matter. And that's why it's called the Neutron Star Extreme Matter Observatory. It will allow us to understand more about this neutron star matter. And so if you're excited about neutron stars, you should totally be on board with NEMO, because I'm excited about neutron stars and I really want to see this happen.
So it's not Finding Nemo, it's Funding Nemo.
Funding Nemo. Yeah.
Funding Nemo.
Disney or Pixar don't come for us. Yes. It's Funding Nemo.
We might grab 2 or 3 more questions.
One from me.
One from you, Chris.
Shanika.
Yeah.
Have we actually found anything using the timing from pulsars yet?
So there was some recent news that that's just completely slipped my mind, but there was a recent publication on this. I would probably have to quickly read up on it and get back to you on that. But there was some recent news on it. I will have to, just re-jog my memory on that.
I think the other thing we might do is I'll do a couple more questions, but then the other ones I might actually get a copy of them and email them to you. And if you can answer them, we can, or if you want to jump onto the Facebook page afterwards and answer them.
No, absolutely.
Yep.
And the questions that I couldn't answer right now, I'm totally able to just come in later and answer them for you.
So David's saying, thank you for an interesting talk. And you mentioned that two black holes merge to form a single larger black hole, and also mentioned the neutron star kilonova merger. Is there a remnant left from a binary neutron star merger, and do they create a black hole?
Great question. So from a binary neutron star merger, depending on the masses of the neutron stars and a couple other things, but masses of the neutron stars, there are multiple scenarios that can happen. You either form a black hole straight away, because when you go beyond a certain point, everything will collapse down to a black hole. You can also get a scenario where it forms a pretty massive neutron star for a short period of time, but it's not very stable. So then again, it will collapse down into a black hole. And finally, you might have a moderately long-lived hypermassive neutron star. So it's a fairly massive neutron star, moderately stable, and it lasts for a fairly long period of time. Not sure if it's for how long, but it probably will collapse down into a black hole. So there are multiple scenarios that can happen, and I'm definitely not a neutron star matter expert in terms of post-merger remnants, but there are a number of colleagues I have at Monash who can help me out with these questions. So I might consult them and get back to you to answer it more completely. But yes, you can form a black hole or a neutron star, potentially.
All right, so last one we'll go to, and then the rest we'll try and get to in the comments. Steve on YouTube wants to know, can a core collapse supernova create gravitational waves? If so, would they be a magnitude that could be detected?
Ooh, yes. So I mentioned on my wish list these that I wanted to see gravitational waves from supernova. We can expect, like, it is in the band that we would expect. It should be detectable with our ground-based interferometers. It's in that frequency band, but it's quite tricky. I can't remember off the top of my head how loud they are, but they're tricky because with gravitational waves from compact binaries, we have a very good understanding of what that waveform should look like. So we can, when we analyze the data, we essentially compare waveforms we have from theory and see which one fits best, essentially, to figure out the properties. But with supernovae, they're more like bursts. It's hard to understand what that waveform or signal will look like. So there are different pipelines that are designed to look for these burst-like signals. And so I'm hoping that one of them will be able to pick up something like this. But yeah, it is in the band of our ground-based interferometers. So potentially we should be detecting them now, but maybe they're too weak. But and we haven't seen any yet, but I'm really hoping we do. So that's pretty much my thoughts on this. I really want to see a supernova.
That one in the work in progress.
Yeah, I want to see this. It's on my wish list.
Now, if anybody else has any questions they'd like Shaneka to answer, we'll try and get her to answer them in the comments on Facebook and YouTube when she has a moment, when she has time to. Before we get into Stefan's tour of the October night sky, just wanted to announce the upcoming event this weekend. We have the International Observe the Moon Night live stream on Saturday night in conjunction with lots of other places around the world as part of NASA's International Observe the Moon Night. If you haven't entered our photo competition, you still have time. You've got tonight, if the clouds are gone, or if the moon's poking out between the clouds, and you've got tomorrow night, and you've got until midnight on Friday night to take your photo and share it on our posts. First prize is a 1-year membership to the ASV, and second prize is a pair of Saxon Night Sky 15x70 binoculars valued at $169.95, courtesy of Saturday night's live stream sponsor Optic Central. So be sure to take your photos if you haven't already. And when you put your photo up in our posts, put the tag of your date and the equipment you used. We also have the upcoming Vic South live stream the weekend before we all get out of proper lockdown and have some freedom. We have a raffle that will be launched tomorrow for that star party. There are 2 prizes. First prize is a Skywatcher Star Adventurer mini kit valued at $699. And second prize is a 40-inch long telescope carry bag valued at $299. And a big thank you to the team at TSA Outdoors for sponsoring the Vic South Star Party. Now, Stefan, I've got dry throat. Chris, do you have anything you'd like to add?
Before we cut to Stefan, I think we owe Shanika a huge vote of thanks.
We do.
Interesting and informative talk. That was fantastic. I know a lot more about gravitational waves and how to detect them and what they are and what you're up to than before. So thank you. Unfortunately, we can't give you a big ovation. It's rather hard coming across.
Look, we can give a virtual applause with all of the comments. Many thanks, Shanika. Proud of you, Shanika. Great presentation. Thank you, Shanika. Good luck with your wish list. Fantastic presentation. It's everywhere.
Nice. Yeah.
So
thank you so much for having me. This has been a lot of fun for me to talk about what I work on.
I like this one. Shanika is an outstanding communicator in a leading edge topic. This talk is a great companion to the discussion with Paul Lasky. I just noticed I just read that. Yes, that was a bit of fun. Lots of people saying thank you. Love your passion. Impressive session. So yes, if there was a crowd, they'd be clapping.
Thank you so much.
Now it's Stefan has the floor.
That's it. And yeah, I'd just like to also personally say thank you so much, Shanika. That was a really, really fascinating talk. And I really like the idea of the pulsar timing arrays. I've never heard of that before, so I've got to look into that. So thanks again for your talk. And so now I'll be covering what's in the sky for this month, October 2021. And apologies in advance. I am an astrophotographer primarily, so everything's a bit biased towards the photography side, but I've tried to balance it out a bit. So starting off within our solar system, I'll cover some of the planets and some of the moons, what's going on this month, and then I'll move into the deep sky objects a little bit later on. So first up, tomorrow night, actually, there's going to be a conjunction between Saturn and the moon. The moon's currently in its waxing gibbous phase, and you'll see them both around 75 degrees in altitude in the north-northwest direction after sunset. And as you'll see, they're really fairly close at around 3.5 degrees separation, making it a really great conjunction to photograph with basically, any lens at approximately 400 millimeters or less. And because, they're so bright, don't even really need a tripod to image them. Then the next night, actually, Jupiter and Moon will have a similar conjunction. Again, the Moon will be in its gibbous phase, as it's only one night later. And a little extra treat, the Great Red Spot will also be visible on Jupiter at this time. They'll be a little bit further separated, around 4 degrees separation, still nice and high, 70 degrees up in the north-northwest sky. So again, if you've got 400 millimeter lens or even the 200 millimeter lens, which I've shown as an overlay here in red. So, even if you've got a modest DSLR setup, get out there and take a shot. It's a really, really beautiful conjunction. Then on the 16th, of course, I've got to promote our International Observe the Moon Night, our live stream again from 8 p.m. Australian Eastern Standard Time. So please join us. Hopefully the clouds will stay away and we'll be able to get some nice views. And so on the 16th, on the Observe the Moon Night, the moon will still be growing in its waxing gibbous phase, but there'll actually be quite a nice alignment between the moon, Jupiter, and Saturn, with a total separation between them of around 28 degrees. So this will be a really, really beautiful thing to get out there and see with your own eyes. And even if you've got something like a really cheap DSLR kit lens with 50 millimeters of focal length, you'll be able to capture all three in the same photograph. So definitely get out there and take a look, and yeah, enjoy it. Zooming in a bit closer onto the moon, this is approximately the phase of the moon that we'll see on the 16th on International Observe the Moon Night. And you might be thinking, it's a bit weird that, International Observe the Moon Night isn't on the night of a full moon. But that's for a very good reason. And that being that when the moon is fully illuminated, when it's a full moon, all of the moon's surface is completely evenly illuminated. And so it can look kind of flat. Whereas when it's in this gibbous phase or a crescent phase, when the terminator of the moon, so the shadow, comes across the face here, all of the craters and all of the mountains in this region are really nicely highlighted. They're all casting long shadows, and it really gives some perspective, some three-dimensionality to the details in this region. And so it's actually a really nice night for International Observe the Moon Night, because the terminator is coming right across this mare here, Mare Imbrium, which I think, personally, to me, is one of the most fascinating structures on the moon. So Mare Imbrium, or the Sea of Rains, is an impact crater that's absolutely massive, 1,140 kilometers in diameter, so large that you can easily see it on the moon with your naked eye. And this was actually formed around 4 billion years ago during the late heavy bombardment stage of the solar system, when the Earth and the moon were still in their infancy, still being bombarded by large extraterrestrial objects. And so this Mare Imbrium here was created by the impact of essentially what amounts to a protoplanet, an asteroid so large that if it formed its own stable orbit, could have become a small planet itself, but instead collided with the moon and left a scar that 4 billion years later we're still seeing the remnants of. And within this region, there are some really, really fascinating structures. The most interesting here is on the lip here of the impact crater, there is what's called Montes Apenninus, or the Apennine mountain range on the moon. This is one of the largest mountain ranges on the moon, and it's a fantastic object to photograph and to look at. As you can see in this photo that I took here, the terminator was coming across Mare Imbrium like it will be on the 16th. And so you can see the shadows cast by all of the mountains within the mountain range. And the coolest mountain within this mountain range is Mons Huygens, named after the famous astronomer Christian Huygens. And this is the single highest peak on the moon at an elevation of around 5.5 kilometers high. And you can see the shadow of the peak just here in this image. So it's a really, really beautiful object to look at, this Mons Huygens. Similarly, in the same region, up in this region here, there's a really, really small structure called Crater Ina, or Ina. I'm not sure how it's pronounced, but us amateurs mostly call it the Blue Lake, because it has a really quite a stunning blue appearance relative to the surrounding moon terrain near it. And I say that it's an imaging challenge because it's an incredibly small structure. As you can see, the scale here is 1 kilometer. So this crater here is only around, I think, 2.5 kilometers in diameter. And this means that you need a really, really large telescope in order to resolve it. Probably something exceeding 10 inches in diameter, something like a 12-inch, 14, or even 16-inch Dobsonian, in order to resolve it at all, or possibly even see the blue. But it has been done with amateur equipment. So if you have, a Dobsonian telescope with a camera, or a large SCT Schmidt Cassegrain telescope, definitely give it a go. See if you can find it. It's a really beautiful and rare target. And one for the observers are these Rilla. Again, not sure how to pronounce it. I think it comes from some Latin word. But these are sort of these worm-like structures that you can see in the surface of the moon. And there are a few different types of these Rilla, and they are formed by different phenomena. But as you can see, they all sort of share a similar shape, sort of like almost like a snake. They're only very, very small in width, only usually like 1 or 2 kilometers in width, but can span many hundreds of kilometers. Because of their very small width, they can be very, very challenging to view through a telescope, especially when the atmosphere is not very stable. But as you can see, this region has a number of them here, and even some here. So, yep, if you've got a nice telescope, a nice big Dobsonian or something, definitely whip it out. If it's nice and clear, try and have a look in this region. And another really interesting object is coming across from Mare Imbrium, this crater here. This is one of the most famous craters on the moon, one of the largest, Copernicus. It's really enormous crater. It's 93 kilometers in diameter, almost 4 kilometers deep, and was formed by the impact of a large asteroid around 800 million years ago. But I just really love this crater because you can see all of the sort of stress fractures imparted by the initial impact, and also all of these pockmarks from secondary impact from some of the ejecta that was spewed out from the initial impact. And also right in the middle of the crater, you can see these uplifts, these central uplifts they're called. They're essentially little mountains left over from when the initial impact happened. There was a sort of splashback effect in the middle. And they may seem small, but these little mountains themselves are like 500 meters high. So it's just a fascinating region. And one challenge, again, for you astrophotographers out there is if you can take a high-resolution photograph like this, what you can actually do is then map your photograph to displacement or height data that's freely available on NASA's website, and you can render your image in 3 dimensions, as I've done here. And seeing it in 3 dimensions can really help you contextualize the relative size of this of the impact craters and some of the mountains. Of course, it's a little exaggerated here, but it's just for viewing effect. So again, the moon is wonderful and it's full of many spectacular features. And if you can join us on our live stream on October 6th from 8 p.m., you'll be able to see it nice and up close. So moving back into other objects in our solar system, on the next night, October the 17th, one of the dwarf planets, Eris, will be at opposition. Eris is actually the 2nd largest dwarf planet. It's got a diameter of around 2,300 kilometers. And that has a highly eccentric orbit, going far, far beyond the orbit of Pluto even. And its period is around 560 years. So 560 years to make one entire orbit. And at the moment, unfortunately, it's near its perihelion, its furthest point from the sun, meaning that it's really, really far away. In fact, 95 astronomical units far away. And because of this, it appears incredibly small. Well, it appears as a point source in our sky, but it also appears incredibly dim at a magnitude of 18.8. However, 18.8 is still within the limits of some amateur astrophotography equipment. And so, with fairly modest equipment like this photographer here has taken with the Skywatcher 10-inch reflector and a QHY9, both commercially available equipment and fairly standard stuff for astrophotographers, he's been able to photograph Eris back in 2017. So if you've got a nice reflector setup, maybe challenge yourself, see if you can actually find this tiny little dwarf planet. You'll find it in the constellation Cetus at an altitude of around 53 degrees, towards the north at around 1 or 2 p.m. Then on the night of the 17th and the night of the 20th, the Orionid meteor shower will be at its peak. This is a meteor shower caused by Halley's Comet, with its radiant or point of origin coming from within the Orion constellation. And you'll see the shooting stars seem to come out from this point. The first minor shower will peak at around on the 17th night, and then the major peak will be on the 20th to 21st. During the major peak, you can expect around 10 to 20 meteors per hour, with some big bright ones, of course. To do this, though, you'll need to get up pretty early in the morning, ideally around 3:30 to 5:30 a.m. before the sun's risen, so that Orion is nice and high in the sky. Unfortunately, on the 20th, the moon will also be out, which means the sky will be brighter, so you won't be able to see or image as many meteors. So you may actually be better off trying to see it on the 17th. Then on October 25th, Mercury will be at its maximum western elongation, meaning its furthest west point away from the sun, meaning that this is the best time to view Mercury because it appears far away from the sun, essentially, whereas for the rest of the year, it appears so close to the sun you can't see it. Still, in saying that, it's only 18 degrees separation from the sun, so you'll have to get up really, really early in the morning just before the sun rises to see it around 10 degrees above the horizon. And of course, Mercury, being so small and so far away, appears very small on our night sky. On this night will only appear around 7 arc seconds in diameter, meaning that you'll need a large telescope in order to resolve it. Ideally, again, something maybe in the range of 8 inches, 10 inches and above. Then on October 29th, Venus will be at its maximum eastern elongation, meaning this will be the best time to see Venus because it's furthest from the sun as it will get. And instead of getting up in the morning and seeing it before the sun rises, this will be best seen just after the sun sets. So on the 29th, it will be approximately 30 to 40 degrees in altitude, depending on when you go out, just after the sun sets in the western sky. And it'll be 50% illuminated. And because Venus is a lot closer to us and it's a larger planet, it will appear a lot larger in the sky, extending around 24 arc seconds in diameter. Meaning even with more modest equipment, maybe like a 6-inch Dobsonian or something, you'll be able to resolve the disk. So definitely best time to view and image Venus. So get out there on the 29th. So moving on to some of the deep sky objects available this month. So in these slides, I'll show 3 main things. One, just a nice pretty photo of the target to give you some idea of what it looks like. Then second, a simulated field of view that you can expect to see with modest astrophotography equipment, like an 8-inch Newtonian reflector with an 800mm focal length, and a very common astronomy camera like the ASI 1600 with its 4/3 sensor. So this is the sort of field of view that you can expect. And then up here, this is the altitude of the object as the night goes on. So you can see in the middle of the darkness here, that's around midnight. And then this is the altitude of the object as the night goes on. So the first object, obviously, is the Helix Nebula. And this is a beautiful, beautiful planetary nebula located in the constellation Aquarius. It's situated around 650 light years away. And it's actually one of the brightest large planetary nebulae in the sky. At magnitude 6.7, even with fairly modest equipment, you can still get a pretty decent photograph of the core. And it's actually quite large as well, with the core extending some 25 arc minutes, basically half a degree, almost the same size as the full moon, right? So it's very bright, very large, a beautiful, beautiful target to try and go out there and image. And as you can see, the core of the nebula is quite bright, but there's a lot of dim extended nebulosity from some of these outer shells, which are really, really quite a nice challenge for us astroimagers. So it's a great target for beginners and intermediate and advanced imagers alike. Next up is NGC 7009, the Saturn Nebula. This is another planetary nebula located in Aquarius at around 2,000 to 4,000 light years away. It's, again, pretty bright, magnitude 8.0, but it is much, much smaller than the Helix Nebula at around 40 arc seconds in diameter. And here in the simulated field of view, I've also added on a 5 times power mate. So essentially multiplying the focal length by 5 times, and you can still see that this object is absolutely tiny. So in order to image this kind of nebula, you might not want to do like long exposures with a wide field setup, but instead try something called lucky imaging, which some of the planetary photographers use because it's such a bright and small object. As you can see, it's a little bit late in the year. Now it's starting to just descend as the night goes on. but still worth a shot if you like planetary nebulae. Another planetary nebula, Robin's Egg Nebula. This one's located in the constellation Fornax at a distance of around 1,500 light years. It's a fair bit dimmer at magnitude 9.4, but it's modestly sized. It's around 10-ish arc minutes in diameter. So a little bit smaller than the Helix Nebula. But it's quite a unique planetary nebula. It's quite sort of aspherical, as you can see. It really resembles the egg from its namesake. And it's got a really, really stunning blue color from ionized oxygen. So it's a really great object to target with narrowband filters. And as you can see, it gets nice and high, 78 degrees at around 3 o'clock. So perfect time to be imaging this nebula. And I apologize, again, another planetary nebula. It's just that sort of awkward in-between time of the year where, you know, the core of the Milky Way is setting, but Orion hasn't risen yet. So we just are looking out into an almost empty patch of night sky where there's only really planetary nebulae and galaxies. But still, there's quite a bit to image. So this one, the Skull Nebula, this is another planetary located in Cetus at a distance of around 1,600 light years. It's sort of brightish at around magnitude 8, but it's fairly small with an apparent size of around 4 arc minutes. As you can see in this modest astro setup, it appears relatively small, but large enough that you can definitely resolve some structure. Again, it gives off a really beautiful sort of bluish hue that really lends itself well to narrowband imaging, like most planetary nebulae. Again, this is an ideal time of the year to image it. It gets nice and high, up at 64 degrees when viewed from Melbourne. Finally, onto the galaxies. NGC 253, the Sculptor Galaxy. This is by far, hands down, one of the most beautiful galaxies that we get to see in the Southern Hemisphere. It's an intermediate spiral galaxy located in Sculptor, of course. It's found at a distance of around 11,400,000 light years away, and it's fairly bright as galaxies go at magnitude 8, and it's also quite large with its length spanning almost half a degree, essentially the length of the full moon. As you can see in our modest setup, it covers a nice, decent chunk of the frame. You'll be able to resolve a lot of detail all the way into the core, as well as a lot of beautiful color. Again, it gets nice and high, 77 degrees, almost right overhead at midnight. Perfect time to be imaging this galaxy. And in addition, galaxies like this can also be enhanced, if you're an imager, if you use a hydrogen alpha filter. There's a lot of little pink emission nebulae embedded within the galaxy, and if you use a hydrogen alpha filter, you can really pull those out and highlight them within the galaxy photo itself. So give that a try if you haven't. So another nice galaxy, NGC 55. This is commonly called the String of Pearls galaxy. It's also found in Sculptor, but it's not a nice spiral galaxy. It's sort of an intermediate barred spiral galaxy with it looks like it's gone through a bit of disturbance in its past. It's a little bit irregular, but it's still quite beautiful. Distance of around 6,500,000 light years, magnitude 8.8, so a bit dimmer than the Sculptor galaxy, but a relatively similar size at around half a degree in length. Again, perfect time to image it, gets directly overhead, right in the middle of the night. A bit of a different galaxy this time, NGC 300. This is the Southern Pinwheel Galaxy. This is a really beautiful, unbarred spiral galaxy, again in the constellation Sculptor. As you can see, this time we're seeing the galaxy almost face-on as opposed to side-on in the previous galaxies. And you can really make out a lot of that beautiful spiral structure. This one's at a distance of around 6 million light years away, magnitude 9, so a fair bit dimmer than the others. You'll definitely need a longer total exposure time in order to bring it out. And it's a little bit smaller, but still relatively modestly sized as far as galaxies go in the Southern Hemisphere. Again, this is another galaxy where there are a lot of little pockets of hydrogen nebulosity, given that this is a really active starburst galaxy. And so if you use a hydrogen alpha filter, you'll be able to pull out a lot of that nice pink hydrogen detail. And really perfect time to image this directly overhead in the middle of the night. So get onto it if you haven't already. Now, a couple of galaxy clusters. One of the most famous, the Grus Quartet. This is a cluster of interacting galaxies in, guess where? The constellation Grus. These are at a distance of around 50 million light years away. And as you can see, there are 4 main galaxies, given the name Quartet, that make up this cluster. And they give this sort of iconic image. And with this modest equipment, you can frame all of them beautifully. Also, if you do decide to image this region, I really encourage you to not just cut short once you've got these galaxies exposed, but push your exposure time a little bit further, because there are dozens and dozens of small dim galaxies off in the background. And if you pull them all forward, it'll make a really, really striking image. Again, perfect time to image this cluster. Another galaxy cluster, NGC 1365 and Co. This is another cluster of galaxies in the constellation Fornax, around 56 million light years away. The main one within this region, NGC 1365, I think it's called the Great Barred Galaxy. I wonder why. It's got a nice, beautiful bar within its galactic nucleus. But as you can see, it's a little bit smaller compared to the other galaxies I've shown, but there are a number of other galaxies that you can see in the background. And it's a fantastic region to image. Image yourself your own Hubble Ultra Deep Field type image. Trust me, there are got to be hundreds of galaxies within the background of this image. It's a little bit early to start imaging this galaxy. It's getting nice and high, but get ahead of schedule, start imaging it as soon as you can. Now, a bit closer to home, our galactic neighbors, starting off with the Large Magellanic Cloud. This is a dwarf irregular galaxy in the constellation Dorado. I'm sure we're all familiar with this one. It's at a distance of around 158,000 light years away. It's one of the companion galaxies of our own Milky Way galaxy, and it's incredibly bright, magnitude 0.7, easily visible to the naked eye, even in suburban areas. But if you get out there in those dark skies, they just really pop out. And the Large Magellanic Cloud, of course, owing to its name, is very, very large. It's over 10 degrees in angular extent, much larger than the full moon. So I'm sure I don't need to sing the praises of the Magellanic Clouds. All of us have probably seen them at one point in our life. So here, this field view, I've actually swapped out the large modest telescope for a much smaller, just full frame DSLR and 100mm lens. So this kind of setup is something that even non-astrophotographers might have laying around. And as you can see, you can image this galaxy just beautifully with this kind of setup. And because it's so bright, you don't really even need a tracking mount to image this. You can set up your DSLR setup on a tripod, take very short exposures and stack them all together and bring out a lot of that detail. It's a little bit early in the year to start imaging the Large Magellanic Cloud. It's only just coming up as the night comes along, but again, get ahead of the schedule. And this is another target that it's great for beginners because it's large and it's bright, but it's also great for advanced photographers. There is a lot of nebulosity in this region, all surrounding the Large Magellanic Cloud. So what you could do is, take a nice wide field image like this of the entire galaxy itself, and then add on some hydrogen alpha, some S2, some O3, really make those nebulae pop. So now zooming in to one particular nebula in the Large Magellanic Cloud. I'm sure all of us down here in the Southern Hemisphere are familiar with this, NGC 2070, the Tarantula Nebula. So this is the largest emission nebula in the Large Magellanic Cloud. It's found within the Large Magellanic Cloud around 160,000 light years away. It's quite bright at magnitude 8, and it's quite large as well, with its parent size stretching around 2/3 of a degree. So as you can see here, this is the core of the Tarantula Nebula. It's incredibly bright. I'm currently imaging this target, and in my single sub-exposures, the core is almost blown out. It's that bright. So again, this is a really great target for beginners because it's nice and big, nice and bright, but also for more intermediate astrophotographers. As you can see, there's a lot of really dim nebulosity here, even some supernovae remnants here that, if you image this region, you can sort of control the bright core and bring out some of the dimmer extended structures. Moving on to our other neighbor, the Small Magellanic Cloud. This is, of course, our other companion dwarf irregular galaxy in the constellations Tucana and Hydrus. This one's a little further at around 203,000 light years away, but it's also really, really bright, magnitude 2.7. Again, you can see it from rural locations with your unaided eye. And it's quite large again, spanning over 5 degrees by 3 degrees on the night sky. So again, with that same full-frame DSLR and 100mm lens, you can capture the entire galaxy in context with the 47 Tucanus globular cluster as well. Really, really great object to target with a wide field setup and a high magnification setup. And it's the perfect time of year to be imaging this. It gets nice and high, 55 degrees, right in the middle of the night. So zooming in to this object here, 47 Tucanae. This is a globular cluster that appears to be in the Small Magellanic Cloud, but it's not. It's way, way, way closer to us, only 13,000 light years away, as opposed to the 200,000 light years that the Small Magellanic Cloud is. So this is really a foreground object. It's really close to us. It's relatively bright too, at a magnitude 4.09, and it's nice and large with an apparent size of half a degree, essentially the same size as the full moon. So it's absolutely fantastic to image for beginners, intermediates, and advanced images alike. And I've got to say, I think personally it is the most beautiful globular cluster in the entire night sky. Omega Centauri is a little bit larger, but this one has some beautiful density towards the core of it that really gives it a really nice shine. And again, perfect time to be imaging this target. Now, zooming in to a nebula within the Small Magellanic Cloud in this region here is NGC 346, as you can see here. This and also some surrounding nebulae are emission nebulae embedded in the Small Magellanic Cloud. Again, these nebulae are incredibly far away, 210,000 light years away, but we can still discern structure within them. Lending to the fact of how large and how energetic these nebulae are. And I'm also currently imaging this region here, and I can tell you there is heaps of hydrogen alpha in this region. So great under-imaged target that I can highly recommend. Again, perfect time of the year to image it. And so thank you, and hopefully the clouds stay away and we have clear skies for the next few weeks, because it's been a pretty miserable winter.
Added to that with lockdown, all we wanted was clear skies, so we would have been happy. Now, Chris, do you have anything else you'd like to add before we wind up for the evening?
Well, I was just going to talk a little about the LMDSS. We will open it as soon as we can, and we will have to obey whatever rules are in place at that time from the chief medical officer. So we will do what we have to. We're training up a great heap of COVID marshals so that we'll have enough COVID marshals to open up. And when you go up there, please do the right thing. Be nice to everybody. It's a difficult time. We're coming out of a difficult time. We need to be nice to each other. So if you're asked to do something, please help out. We are a society. We're run by volunteers. We need cooperation from everybody to make things work. So we will open up as soon as we can. We'll run everything back as normal as we can. So that's it from me. Thank you, Stefan. That was very interesting. And again, thank you, Shanika, for a great talk. Sorry, I stumped you with that one about about pulsars, but I guess that's par for the course.
I'm sure you'll get a response soon enough that'll knock your socks off with an answer. To everyone else, to those who have been sitting and watching the stream tonight and enjoying it, thank you for joining us for tonight's presentation. And Shanika, thank you very much for such an amazing presentation. It was absolutely engaging. We hope everyone enjoyed tonight. And if you're not yet a member, but you're interested in becoming a member, please go to www.asv.org.au/join. And if you don't follow us on Facebook yet, please give us a like. And if you're watching us on YouTube, please subscribe to our channel. And remember that we will see you on Saturday night for International Observe the Moon night, which kicks off at 8 o'clock on Saturday night. And we look forward to seeing you then. Till then, please, guys.
Good night.